Hello guys, welcome back to another video, another episode of Consultant Explains Maths. Today I want to talk about another question that I encountered when I was a sophomore. I encountered this question in a test for Introduction to Proofs. So it'll be quite simple. So the problem statement is simply to prove that the square of 3n plus 2 is irrational. For all natural numbers n. Okay, yeah, the problem is simply to prove that this statement holds. And I was not able to solve this during a test. I actually asked one of my friends after the test, and he gave me like a very clear explanation as to why that is the case. But I kind of forgot about it. I just didn't remember to. I just didn't really bother to remember the key steps to doing this. And then this problem just suddenly popped up in my head again, 5 years after I faced this question. And yeah, I miss my full-time job. I feel like, yeah, it's fun to just try to solve this problem. It's kind of weird. Anyways, uh, I came back with a lot more resources, and this resource coming from in the form of a Reddit post. In fact, I actually tried to solve this, and I wasn't actually able to do it because I was just horrible at number theory stuff. I don't know if it's number theory or not. It's just basic proving really. But yeah, basically if it has to do with numbers, if it has anything to do with theory of numbers, I'm just horrible at them. Anyways, I asked this on Reddit, and I'm going to link you to the Reddit post I wrote. And indeed, it has been resolved. It's been resolved. And yeah, let's just get started. So this isn't really my attempt. There's already a complete proof, as far as I know, incorporating the solution or the hints actually found in Reddit post. Okay, let's get started. So to prove that the square root of 3n plus 2 is irrational, we can try the good old trick that is proof by contradiction. So if we want to make a contradiction, we first suppose that there exists a natural number n and then integers a and b such that square root of 3n plus 2 can be expressed as a fraction a over b, where both a and b are co-prime, or in other words, have greatest common divisor of 1. Okay, from here we can square both sides. So we have 3n plus 2 equals a squared plus b squared. And then we just rearrange this into a squared equals b squared times 3n plus 2. Now notice this last line here. We have a squared equals b squared times 3n plus 2. If we just assume that this form right here is m, an integer, then we can say that b squared divides a squared. And then by simple theorem regarding powers of integers, or the powers of numbers, I'm not sure if it only holds for integers. I think only integers anyways, divisible. All right, so because of this, there's actually a proof that b is divisible by a, and this is probably not too far off from something that someone in a introductory course of proving need to know. And I probably didn't. Again, this is something you will see in number theory. Very basic, but I somehow forgot. Anyways, from this point, we see that B divides A, so we can write A to be equal to the, maybe got M there, so KB with K an integer. But remember, because A and B are co-prime, then if B does divide A, that is, B is a factor of A, then B is necessarily 1. It's quite easy to see by that. So we plug that into this form and obtain another observation that if the square root of 3n plus 2 were indeed a rational number, it actually has to be an integer. So yes, it is a rational number, but with the denominator being 1. So we have to prove that the square root of 3n plus 2 is an integer if it were a rational number. And now here we're going to check a case-by-case proof of what would happen if you square a number in relation to its congruence mod 3. Or in other words, if you square a number, we have to take a look at what its remainder would be if we divide such said squared number by 3. So we have to divide this into 3 cases. That is, we try if A is either congruent to 0 mod 3, in other words, it is a multiple of 3, or you can try if A is congruent to 1 mod 3, and then it also can be congruent to 2 mod 3. So each of these mean that A is congruent to 0 mod 3 means that A is equal to 3L, and then for the second one here, A is equal to 3L plus 1, and then same goes here. And this all assumes L is an integer. So now we plug this in and see if we can get the desired form. So basically here we attempt to square the number A. So if A is congruent to 0 mod 3, then A squared is equal to 9L squared, which is equal to 3 times 3L squared. And this is a multiple of 3. So in this case, A squared is congruent to 0 mod 3. If A is congruent to 1 mod 3, which means that A is equal to 3L plus 1, we can work it out and obtain A squared is equal to 9L squared plus 6L plus 1. And then we can rearrange this. We can group the factors of the first 2 terms, which is 3. So here's 3L squared plus 2L plus 1. And this means that when squared, so that means if A is congruent to 1 mod 3, A squared is congruent to 1 mod 3, because this is of the form of 3 times some integer, remember that L is also an integer, plus 1. So A squared is, congruent to 0. Again, 1 mod 3. One case remains, and that is, what if A is congruent to 2 mod 3? So instead of 3L plus 1, it is equal to 3L plus 2 for some integer L. So again, work it out to obtain 3L squared plus 2 times 3, 12L plus 4. Again, we can factor out 3 from the first two terms, leaving us with 3L, 3 times 3L squared plus 4L plus 4. But notice that plus 4 can also be decomposed into 3 plus 1. So 3L squared plus 4L plus, I'm just going to do this, I'm just going to skip this line. So it's supposed to be a plus 3 plus 2. So you can factor out 3 here, and then you get 3L squared plus 4L plus 1 plus 1. And this is of the form 3 times some integer plus 1, which means that in this case, a squared is congruent to 1 mod 3. And remember, any integer that we have all must fall into one of these categories. So an integer is either divisible by 3, leaves the remainder by 1, of 1 when divided by 3, or leaves the remainder of 2, and no other cases. So we've exhausted all the cases of an integer. And then when we square each case, when we square a number of each case, we obtain the following. So it can only be congruent mod 0. In fact, it shouldn't be mod 2, as spoiled it, or congruent to 1 mod 3. But none of them are congruent to 2 mod 3, which we need. Because, again, here, 3n plus 2 equals a squared means that somehow 3n must be a squared minus 2. Or rather, a squared must be congruent to 2 mod 3. But we have proven that by exhausting all the cases, that this is actually impossible. And there we have it. There's a contradiction. If it were a square of 3n plus 2 were indeed a rational number, and actually the only kind of rational number it can be is an integer, then we would not actually get something that when squared is congruent to 2 mod 3, because any integer when squared would only be, any integer when squared would only leave a square that is congruent to either 0 or 1 mod 3. So because of this, we have reached a contradiction. And yeah, okay, sorry, this is all over the place, I know. So this means that the square of 3n plus 2 cannot be an integer, and therefore cannot be a rational number. And we've proven it. Yeah, that's the end of the proof. Again, I could not solve this in the exam. That was horrible. Maybe it's just that I was so time constrained and my ideas I just couldn't express my ideas fast enough. Or maybe I was just running out of ideas way too quickly back in the day. But yeah, there you have it. We know that square of 3n plus 2 is indeed irrational. So yeah, that's all from me for this video. Hope you guys enjoy it. I'm going to leave a link to a post I wrote where I've asked for help at Reddit. Okay, thank you for your attention. Bye.